our last unit focuses on differential equations. So we've already talked a lot about derivatives and integrals. So we're going to talk about specific sets of equations that have one or more differentials in them and different types and how to solve them. So a differential equation is simply an equation that has derivatives within it. Okay? That's probably the easiest way that I can describe it. But, unlike what we've done in the past, where we have something like, y equals x squared, so dy by dx is equal to 2x, that is considered a differential equation, but you can also have different versions of that. So you could have an equation that has second derivatives and first derivatives in it as an example, okay? So I've given us a few examples, and each type of differential equation is classified by two items, okay? The order of the equation is the highest order derivative. So if you have a first derivative and a second derivative in the equation, it's a second order differential equation. The second is known as the degree that we classify it as, and that's the largest power or exponent of the highest derivative. Keywords there are of the highest derivative. Okay, so if we look at a few examples of this, these are all in this table forms of differential equations. So if we have dy by dx plus x equals y, okay, that's a differential equation, has a derivative in it. It's first order because it has the first derivative only. And it's first degree because the exponent of that derivative function is simply 1. Okay. Our second example, d squared y by dx squared, which is the second derivative, right? That's the same as seeing f double prime of x or y double prime. Okay, all of those represent the second order derivative. In this case, it's derivative with respect to x plus y equals 3x squared. Now in this case, it is a second order differential equation because it's the second derivative, and it's a first degree differential equation. Okay, and that's because again, the exponent on this squared term, or on this second derivative term, is 1. It doesn't matter that there's an x squared term here. It only matters in terms of the exponent on the highest order derivative. Our third example, d squared y by dx squared plus dy by dx to the exponent 4 minus y equals 6. This is a second order equation because again we have a second derivative here, but it's only first degree, okay? And that's because the exponent of our highest order derivative is 1. It doesn't matter that the exponent on the first derivative is to the exponent 4. Okay, it's still considered a first degree differential equation. So it would, if you're talking about naming these, it would be a second order first degree differential equation. That's how you would say it. Our last example, dy by dx cubed minus y equals 3x plus 5. It's a first order differential equation because we only have the first derivative here. And it's a third degree differential equation because the highest order derivative, which is the first derivative, has the exponent 3. Now, one thing I'll tell you is that we are going to focus on first degree differential equations only, okay? But you can kind of disregard this at this point. But I do like to show you it just so you understand what a third degree or second degree differential equation might look like. In order to find a solution to a differential equation, it's simply an equation that satisfies the differential equation. And what I mean by that is, let's look at this example. Okay, we have a differential equation here that says x times dy by dx minus y is equal to x squared. This is a first order and first degree differential equation. okay, because it has only the first derivative and it's raised to the exponent 1. Now we can show that a solution to this differential equation is this equation here, y equals 3x plus x squared. And we can do it using what we know about derivatives and simple algebra. So we know what y is in this function, and we can find dy by dx by simply taking the derivative of this function. Okay, so the derivative of that function, if we have y equals 3x plus x squared, dy by dx is simply the derivative of each of these two terms, which is 3 plus 2x. So knowing those two terms, we can substitute them in, and using algebra, you determine, again, does the left side equal the right side? It's as simple as that. If it does, then this is, in fact, a solution to that differential equation. So if I substitute these in, I get x times 3 plus 2x minus, in this case for y, 3x plus x squared, and that's equal to x squared. So if I multiply this out, I get that 3x plus 2x squared minus 3x minus x squared must be equal to x squared. And again, that's in order for this to be a solution of the differential equation. We'll see that the 3x's cancel, and 2x squared minus x squared is simply x squared. So we have x squared is equal to x squared. So that means that this equation is a solution to the differential equation. It's actually known as a particular solution because the constants behind each of these variables here are known. Okay, so we have the constant is 3 behind the x term and 1 behind the x squared term. If you had it written as y equals a times x plus b times x squared, remembering back to our partial fractions, that is known as a general solution. Okay, we'll get into what that is in our next slide, but it's general because we don't know what those constants are. Okay, a and b could be any number, but in this case, this specific equation would always satisfy a differential equation. So that's why it's known as general. With a particular solution, it's specific to those particular constants satisfying it. All right. So like I mentioned in the previous slide, there's two basic types of solutions to differential equations, particular and general solutions. So going back to our last example, we had y equals 3x plus x squared. That was a particular solution for this equation, x times dy by dx minus y equals x squared. The reason it's particular is because the constants are defined. Okay, so the constants are 3 behind the x term and a 1 behind the x squared term. Okay, but that same equation, y equals a times x plus b times x squared, where a and b are constants, is still a solution for specific values of a and b, but in this case it's called a general solution because those constants are not defined. Okay, so in both those situations they can be solutions to this same equation. Okay, and there's other solutions to that equation other than just 3x plus x squared. Okay, so that is where the general solution comes in handy. Okay, so you can use different solutions to this equation to obtain different final equations. Okay, so let's look at a few more examples just to familiarize you with both the particular and the general solution and how to kind of see whether or not these equations are satisfied. So our first example determine whether the given equation is a solution to the differential equation, and if so, state whether it is a general or particular solution. So this is the differential equation. Okay, you'll see that it has a first order derivative to the exponent 1. So this is a first order, first degree differential equation. And I write that just because I want to start familiarizing you with the different orders of equations. As we do additional lessons in this unit, we're going to go over how to solve for different types and orders of differential equations, okay? And this is what we're trying to figure out whether or not it is a solution of this differential equation. Okay, so this is how a lot of these style of questions would usually be worded. Okay, and it would usually you can, in this instance for this lesson, you have a solution and a differential equation. So we have what y is. We can solve for what dy by dx is by taking the derivative of this equation. So the derivative is e to the negative x squared times the derivative of the exponent, which in this case would be negative 2x. So that means this derivative comes out to negative 2x e to the negative x squared. Okay. Now substituting the value for y in and the value for dy by dx, we get negative 2x e to the negative x squared plus 2x times e to the negative x squared, substituting in the equation for y, equals 0. So you'll see that these are the same terms, negative 2x e to the negative x squared plus 2x e to the negative x squared. So they cancel, and you get 0 equals 0. So the answer is yes, this is a solution. And since there isn't any general term behind this e function, okay, that means that the constant is assumed to be 1. So this is actually a particular solution. All right. Our second example, again, determine whether the given equation is a solution to the differential equation, and if so, state whether it is a general or particular solution. So our differential equation is dy by dx times ln of x is equal to y over x. And since this is a first order derivative only, we have a first order, first degree, because the exponent here is simply 1, differential equation. The equation that we're going to find out whether it's a solution of it is y equals c times ln of x. So the first item I note here is there isn't a number behind the ln of x term, it's just a constant value c. So we know right off the bat that this is a general solution, if it is a solution at all, because it does not specify a specific constant behind it. Okay? So we have the equation for y, finding dy by dx. It's equal to the constant c times the derivative of ln x, okay, which is 1 divided by x, okay, because there's just x in the ln function, so we don't have any other pieces to this derivative. So that comes out to c divided by x. So if I substitute these values in, we have dy by dx is c divided by x times ln of x. And that's equal to the function y, which is c times ln of x divided by x. So you'll see that the left-hand side equals the right-hand side. So yes, this is a solution. And remember, since we do not have a constant c defined here, it's just c, it is a general solution. Right? So our third example here, okay, has a little bit different items in terms of derivatives. We have d squared y by dx squared plus 4y is equal to 8. So we have a second order derivative here, again raised to the exponent 1. So this is known as a second order first degree differential equation. I really want you to get used to being able to differentiate what each one is very quickly. So get used to kind of looking at them that way first. Our equation we're going to test is y equals c times sine of 2x plus 3 cosine of 2x plus 2. So the first thing to note here is that we have a constant that is undefined, okay? And then that's on the first term because we have c times sine of x. And the remaining terms all have constants that are defined, right? But it doesn't matter, okay? For it to be a general solution, it has to have constants behind these that are not defined, okay? So this is not a general solution. It's in fact a particular solution because we do have some constants defined. A general solution only works if there's multiple combinations of constants that would solve this equation. But really, there's only one constant that's going to be modified here, right? So there's going to be a single solution to it. So a little bit confusing to kind of get to know that, but this example really showed you that difference. So just like we've done in the past, we have the y equation, but we need, in this case, the second derivative. So we can find the first derivative, dy by dx, and that's equal to the derivative of the first term, which is c times cosine of 2x times the derivative of what's inside the sine function back here, which is 2, plus 3 times the derivative of cosine, which is negative sine of 2x, again multiplied by the derivative of the term inside the cosine here, which is 2. And then the derivative of the constant is just simply 0. Simplifying this, we get 2 times c cosine of 2x minus 6 sine of 2x. Now looking for the second derivative, d squared y by dx squared, we get the first term, which is 2 times c times negative sine of 2x, again times the derivative of the term inside the trig function, which is 2, minus 6 cosine of 2x, again times the derivative within that sine function, which is 2. Simplifying this, we get negative 4c sine of 2x minus 12 cosine of 2x. So substituting each of these values in, okay, I'll move this down to here to give us some more space. We have substituting in d squared y by dx squared, we get negative 4c sine of 2x minus 12 cosine of 2x plus 4 times the y function, c sine of 2x plus 3 cosine of 2x plus 2. And that all has to equal 8. Okay? Simplifying this by distributing the 4 into each of those terms, we get negative 4c sine of 2x minus 12 cosine of 2x plus 4c sine of 2x plus 12 cosine of 2x plus 8 has to equal 8. So a couple terms are going to start canceling. Negative 4c sine 2x and plus 4c sine 2x. Negative 12 cosine of 2x and plus 12 cosine of 2x. So we're left with just 8 equals 8. So yes, this is a solution because it equals. And remember, because we only had one constant there, that was arbitrary, it's in fact a particular solution. Okay? Okay, so now that we've talked about different types of differential equations and how to look for general and particular solutions and whether an equation satisfies a differential equation, we're now going to look at the first method for determining solutions to differential equations. In other words, but previously you were given a function that had, a dy by dx plus 4x equals y, something like that. And you were always given what the function y was equal to. Okay, so y was equal to something, 2x squared plus 4, something like that. The question, or the method I'm going to teach you, is one of the ways where you're going to figure out what this function y is. So determining it using a series of methods. This first method is for first order, first degree differential equations. So this equation that I happen to make up while making this recording is actually first order because it only has the first derivative, and first degree because that is only raised to the exponent 1. So it's this method called separation of variables is used to solve these equations. And what the basic premise of it is that a separable equation is a first order differential equation where you can separate the two variables. Typically we call them x and y. So you end up with all the terms with x on one side of the equation and all the terms with y on the other side. This is just like if you remember where we did substitution and we let some u equal some function, let's say it was x, and the derivative du by dx in this case would be equal to 1. So remember, we could separate the du and the dx terms. We could move the dx term to the other side. So in this case, du would be equal to dx. We're going to use that very same principle here in order to be able to solve differential equations using separation of variables. So looking at this as a general term, if we have the derivative of a function, dy by dx, and it's equal to some function of x times some function of y, an example of this would be if you had dy by dx is simply equal to x times y. This x term would be the f at x term, and y would be the g at y term. Okay, so on the left-hand side of the equation, we have a dy and a dx. On the right side of the equation, we have both an x and a y term. Okay, but if we take this in steps, remember back to our substitution that I showed you here. You could move the dx to the other side of the equation. And if you do that, you get that dy is equal to x times y times dx. Well, now you're almost there. We have all the x terms on the right-hand side, but we also have a y term. So our last step would be to move the y term to the other side of the equation. We would do that by dividing both sides by y. And we get 1 over y times dy is just equal to x dx. So now you can see we have all the y terms on one side, all the x terms on the other side. In the general form, okay, we do the same thing. We take that g of y term, okay, and we move it to the other side. And we take the dx term and we move it to the opposite side. So in the general case, we have dy divided by that function of y, or if you want to look at it in our example, dy divided by y, and it's equal to the function of x times dx. Now, when you look at this, it may not immediately stand out to you, but remember when we talked about integrals, we had the integral of some function with a dx beside it all the time. So looking at this, it looks very similar to an integral. And to be honest, that's exactly what we need to do. Okay? So looking at this function, okay, the general function we had was dy but divided by the function of y is equal to f of x times dx. Remember in our example, we had 1 over y times dy is equal to x times dx. Now, if we want to solve for this, or solve for this function y, remember, we can do it by integrating both sides, because we have a dy and a dx term. If we do that in our example, okay, the integral of 1 over y times dy would be the ln of y, and that would be equal to the integral of x is 1/2 x squared. Okay, so our derivative terms are now gone, and we just have functions of y and x. So this method is what we use to solve for first order differential equations. Okay, so I showed you here an example just to kind of make this general term here make more sense. Okay, but we take the integral of all the y terms on one side, and it's equal to the integral of all the x terms on the other side. So keep that in mind when we start looking at our upcoming examples. Okay. So our first example is solve dy by dx equals x divided by y squared. So remember, our first goal is to get all of the y terms on one side, all of the x terms on the other side of the equation. So we can see a couple items here. Okay, we have a dy by dx. I'll rewrite it just so that we can manipulate it. And it's equal to x divided by y squared. So we can take this dx term and move it to the other side by multiplying. And the same goes for this y squared term. We can move it to this side of the equation by multiplying. If we do that, okay, in essence, we end up with y squared times dy is equal to x times dx. Okay, some of you might call that cross multiplying. Okay, when you're multiplying across both sides of the equation. Now remember, we're trying to find the functions that we started with. To do that, now we have to integrate both sides. Now that we've separated the variables, we can take the integrals of both sides. If we do that, remember for this expression, we're using the power rule. So the integral of x to the n dx is 1 over n plus 1, x to the n plus 1, plus a constant. Okay? So we're going to make sure that we include the constant in this. And when we get to our final example in this lesson, you'll see why something like that is important. So if we take the integral, on the first side, on the y side, we get 1 over 2 plus 1, y to the 2 plus 1, is equal to 1 over 1 plus 1, x to the 1 plus 1. And I'm going to add a constant. Now, you can add the constant to either side. It really doesn't matter. right? And it also doesn't matter if the constant's positive or negative, because all of that comes out at the end because the constant is just a number, okay? So if you have it showing as minus the constant, well then if the number needs to be positive, the constant value you calculate would end up being negative to cancel out that negative, okay? It's just a number, so it doesn't matter if it's plus or minus or whatever it is, as long as you have a constant. Simplifying this, we get 1 over 3 y cubed is equal to 1/2 x squared plus a constant. Or if you really wanted to simplify it, you could put the constant on one side and you get 1/3 y cubed minus 1/2 x squared is equal to a constant. It really doesn't matter how you come up with these as your final kind of form. You don't have to have it so one of them is just y and one of them is just x. Okay, it can be in a form like this because this now is a solution. Okay, it's not a necessarily a particular solution because we don't have the constant calculated yet. Okay, so our second example. We don't always have to have dy by dx given in that form. We could have it given in a different form like we do here. We have 2 times ln of x dx plus x times dy, and that's equal to 0. Okay, so we have an x term within both of these terms here, and we have just a dy. So my first step is going to move the dy term to the other side of the equation. If we do that, we get 2 times ln of x dx is equal to negative x times dy. Okay, so now we have almost all of the x terms on the left-hand side, except for this negative x here. Now you don't have to take the negative with you, I'm just choosing to. But if I want to solve now, I can divide both sides by negative x. Since they cancel on the right-hand side, we get negative 2 ln of x divided by x dx is equal to dy. Okay. Now to solve for this, we take the integral of both sides. Okay. So I always like to move the constants outside of the integral, meaning we get negative 2 times the integral of ln x over x is equal to the integral of dy. Now to solve for this, we have a ln x and a 1 over x term. So the first item I always like to use when we have two variables, or try to use, would be to try using substitution. So I'm going to let u equal ln of x. So du by dx would simply be 1 over x. Or remember, and we're using this again for differential equations, we can solve for just du by moving the dx to the other side. And we get du is 1 over x dx. So you'll see that it's going to cancel out that 1 over x term. What we end up with here is negative 2 times the integral of just u times du. And that's equal to the integral of dy. So just for some space, taking the integral of these, on the left-hand side we have negative 2, because that's outside of the integral, times 1 divided by 1 plus 1, u to the 1 plus 1, plus a constant in this case. You can put it on either side, like I said, it doesn't matter. And that's equal to the integral of dy is simply y. Okay? So simplifying this and substituting back in ln of x for u, we have negative 2 divided by 2 is just negative 1. So we get negative times u squared, which is ln of x squared, plus a constant is therefore equal to y. Okay, so this is our solution to the differential equation. Again, we don't know what the constant is, but the next example I'm going to show you how we get a particular solution by solving for the constant. So our last example, okay, this is to look at finding a particular solution, because again, we're trying to find the solution to this, and it's at a specific point. Okay, so when you see the question worded with a specific point, you know that you're going to solve for that constant. So solve x squared plus 1 squared dy plus 4x dx equals 0 when x equals 1 and y equals 3. So consider the x equals 1 and y equals 3 to be just like when you had bounds on an integral. Let's say the bounds are from 0 to 1. You knew that when you had bounds, that with that, you normally were getting kind of a final solution that was a number. You're going to get that here as well. So you consider those as allowing you to solve for this constant, which again, because we now do not just have an arbitrary value, c, for the constant, it ends up being a particular solution. Okay? So let's start by writing out the equation again. X squared plus 1 squared dy plus 4x dx is equal to 0. So we have both the dy and the dx on the left-hand side. I'm going to choose to move the 4x dx term to the right-hand side. So we end up with x squared plus 1 squared dy is equal to negative 4x times dx. So now, to solve, to just have dy on the left-hand side, I have to move the x squared plus 1 squared term to the other side. I do that by dividing both sides by that term. And since they cancel on the left, we're left with dy is equal to negative 4x times dx divided by x squared plus 1 all squared. So now remember, now that we have all the x terms on one side and the y terms on the other side, we can now integrate. So we take the integral of both sides. And in this case, again, when you have terms like you have here, where you have the x in the numerator and you have an x squared term in the denominator, it's always a good starting or a choice to start by trying substitution. So in this case, remember, you usually use the value that's inside the brackets raised to an exponent. If you remember from our first lesson where we looked at substitution. So I'm going to let u be equal to x squared plus 1, or in other words, the term inside those brackets. So du by dx is equal to 2x, or du is equal to 2x dx. Okay? So obviously, here we have a negative 4 here, so we can't substitute for all of it, but we can substitute for 2. And what that leaves us with is the integral of dy is equal to the integral of, removing 2 from this, we end up with just negative 2 divided by u squared du. Okay, so that's just substituting in our value for u and our value for du. Okay. Now, the last thing I like to do, if you remember, I always like to take the constant out. So we have the integral of dy is equal to negative 2 times the integral of 1 over u squared du. Alternatively, you can write this, instead of 1 over u squared, you can write it as u to the negative 2 du, moving that term into the numerator. I like to do that to make the integral process easier, because you can use the power rule directly. So if we do this, the integral of dy is simply y, and that's equal to negative 2 times the integral is 1 divided by negative 2 plus 1. Okay, again, remember to take the exponent and add 1, times u to the negative 2 plus 1. And again, that's plus a constant. So solving for this, here we have a negative 2 in the numerator and a negative 1 in the denominator. That becomes positive 2. And our u term becomes u to the negative 1. So substituting in the value of u, which is x squared plus 1, we get that y is equal to 2 divided by u, which is x squared plus 1, plus a constant. So now we can solve for this constant, making this a particular solution, because we're looking for the solution when x and y are known. So x is 1 and y is 3. So substituting those values in, we substitute y is equal to 3, and that's equal to 2 divided by x, which is 1 squared plus 1 plus a constant. So 2 divided by 1 plus 1 is 2 divided by 2, or 1. So we get 3 is equal to 1 plus a constant, or that means the constant must be equal to 2, right? Moving the 1 to the other side. So our final equation would therefore be y is equal to 2 divided by x squared plus 1 plus 2. Okay? And this is known as a particular solution because it does not have the constant in it. Okay? So the previous examples we looked at in the first part of this lesson had, in some instances, were second order equations. That usually means you end up with two constants. Because if you remember, if you have a second order function, you have to integrate twice, meaning each time you integrate, you have a constant. If you have a first order equation, when you integrate, you only end up with one constant, okay, versus the two constants that are with a second order. So that's why once we solve for this constant, it becomes a particular solution. So that was all I had for your first lesson. There's going to be multiple lessons in this last unit, all focusing on different types of differential equations, different methods for solving. Again, most of these I keep for you in a formula sheet. Okay, so knowing some of the basics of them will be items that would typically be included in your formula sheet. So if you have any questions on these practice problems, please send me a Teams message or send me an email. I'll be happy to help you. Thanks, everybody.